Hi, my name is Samir, and today I'll be talking about our work on continuous scene representations for embodied AI. In recent years, visual scene graphs have emerged as a way to abstract image content into a set of discrete objects and relationships. For example, in this image, the in relationship between the sponge and the sink can be modeled as a directed edge from a sponge node to a sink node. However, these discrete relationships can be too coarse for downstream embodied tasks. For example, an agent must execute a different sequence of actions to manipulate the sponge depending on its location. Hence, we want to move towards more continuous feature representations of these relationships, which encode more fine-grained information. Typical scene graphs operate on a single image or a video and do not have update mechanisms to accommodate newly observed objects or displace objects. As objects and the agents move, we may need to update the graph topology and propagate these relationships. Based on this motivation, we identify a set of needs around which we design our approach, continuous scene representations, or CSR for short. First, we need to extract objects and relationships from a single image. Second, we require a sensible representation for these objects and relationships. Recall that we want continuous representations that capture useful information for embodied tasks. Third, considering the sequential nature of embodied interaction, we also need to be able to update CSR on the fly to accommodate new observations. Finally, we would like to use CSR for downstream embodied tasks as a plug-and-play component for applications. To extract objects and relationships from a single frame, we design around a CSR encoder. Using a faster RCNN model to extract objects from the image, we create n-squared inputs to our encoder, one for each pair of boxes. Each input is 5 channels with RGB, a 4th channel containing a box mask, and a 5th channel with a second box mask. The pair of boxes gives information about what relationship the encoder should consider in the image. The encoder maps the 5-channel inputs to a CSR embedding space. When 4th and 5th channels contain the same box, the features are object features. Otherwise, they are edge features encoding the relationship. What is a good objective to train CSR encoders such that they capture salient relationships? Our insight is to use multi-view consistency for mining positives in a contrastive loss. As an agent moves from view A to view B, the relationship between the highlighted objects does not change. Hence, their feature representations should be close. Additionally, this relationship should be different than other relationships between objects. We reason that enforcing such an objective should encourage learning view-independent relationships between objects. Given a CSR for the current frame and a CSR aggregated over previous frames, we want to integrate the information from the current frame into the aggregated representation. To do so, we design a matching function. This function leverages the fact that our contrastive loss encourages features corresponding to the same relationship to have high cosine similarity. Hence, cosine similarity can be used to match features and add new ones, thereby updating the representation. As an embodied agent moves in a scene visiting different positions, it is possible to evolve the CSR over time. By keeping track of what objects are seen at each agent position, it is possible to ground the relationships in the agent's egocentric observations. In this diagram, green arrows show what objects are seen from each agent position. By connecting the representation to embodiment in this way, we can do new downstream tasks using planning frameworks without additional training. We implement a planning pipeline around CSR for the challenging downstream task of two-phase visual room rearrangement. In this task, an agent must build a representation of a space through exploration and then return misplaced objects. Looking at the results, we see that CSR outperforms sophisticated map-based RL baselines that are trained directly on the task. These trends hold both in terms of the number of rooms successfully rearranged and in terms of the number of objects correctly returned. Thank you for watching.